Hi everyone. So in lesson 10.3, we're going to learn about chords and how they relate to their corresponding arcs. So for your foldable, we're actually going to start on the inside because that is where all your theorems are. So go ahead and open it up to the inside. So our first thing is the definition of a chord. And a chord is where it's a segment inside a circle where both endpoints are on the circle, but it doesn't go through the center, so it's not a diameter. Okay, so something like that. I mean, there's an infinite amount of chords we can draw inside there as long as it has both ends on the circle and doesn't touch the center. So our first theorem says that if we have congruent central angles, remember we learned about central angles in 10.1, then that means that the arcs that they make are also going to be congruent, which makes a lot of sense from 10.1 because the central angle equaled the arc. So if the angles are congruent, then their arcs are congruent. So in the next theorem, if we have congruent central angles, then the chords, so the lines that would connect the angles, would also be congruent. So they have congruent central angles, congruent chords, and congruent arcs. And the converse is also true for those, so that means if you know you have congruent arcs, and then that means their angles are congruent, and vice versa. So this is like the third part of that, like what I just said. If we have congruent chords, we have congruent arcs. So all three of those theorems kind of are saying similar things, just about all the pieces. So if their angles are congruent, then their arcs and chords are congruent. Okay, so the next one tells us about if we have, let me zoom in a little bit. If we have chords that are equal distance from the center, so remember distance is represented perpendicularly, so it has to have the right angle to show you that those two pieces in the middle are their distance. So if their distance from the center is the same, then those chords have to be congruent. Okay, so our next theorem says that if we have a diameter that's perpendicular to a chord, then it bisects the chord, so those pieces of chord are congruent, and it bisects the arc. So it makes all those pieces congruent, but it has to be perpendicular to do that. Next, we have that if it bisects a chord, then it's perpendicular to that chord, so it's the converse of that one. So if we're bisecting it, it has to be perpendicular, so going backwards from what this one says. And our last theorem tells us that if we have a segment that's a perpendicular bisector to a chord, then it's going to end up going through the center. So we know that it'll touch the center if we extend that line. Okay, so let's look at the front and try our examples for this. So for number one, it asks us to find the length of the chord that's right here, X. And we can see that the chord is equal distance to the center from that in that chord. They're both equal distance from the center because they're both 9. So that means that those two chords are going to be congruent. So they told us that this part of the chord is 12.5. So that means that the whole segment would be 2 times 12.5 or 12.5 plus 12.5. So X is 12.5 times 2. So we get that the whole chord would be 25. So take a look at the second one. What are they telling us with that one? So we have that both of the chords are congruent. So if both of the chords are congruent, then what do we know about their distances from the center? They have to be congruent, so X would just be 16. Okay, so we're going to do question 3 last because that's the hardest one. So let's take a look at question 4. So here they want us to find the value of X. X is a radius of the circle. This 14 represents a chord, and the 3 is the distance to the chord. So we know that if it's perpendicular, like the diameter or this piece segment right here is perpendicular to a chord, it goes through the center, then it's going to bisect that chord. So that means that this piece here would just be 7. So if we're trying to figure out what the radius is, we have a right triangle. So what's the method we can use? Very good, Pythagorean theorem. So 3 squared plus 7 squared equals x squared. Remember, the c is always the hypotenuse across from the 90. So then we can just solve that to get what the radius is. So we would have 9 plus 49 equals x squared. So 58 equals x squared, and then we take the square root. So x would equal the square root of 58, which is approximately 7.6, because it said to round to the nearest tenth. So you can type that in your calculator and get your answer. So for number 5, it's the same idea as number 4, except they give us a little bit of different things to start with. So I know it doesn't look like we have a right triangle there, but remember, in your circle, any radius you draw is going to be congruent. So they told us this radius is 15, so I can draw a radius in there to make a triangle, and that radius is going to be 15 as well. I could have also done it on this side. Doesn't matter because all those radiuses are 15. So it shows us that it's bisected this time instead of showing us that it was perpendicular, but remember they're converses of each other. So if it's bisected, then it's going to have to be perpendicular. So we do have our right triangle. So this time they start us with the hypotenuse, or we're given the hypotenuse, and we have to solve for one of the sides. So I'm going to go with A, B, and then 15 is going to be the C. So if we square our numbers, then what would we do next? Good, we would minus this. So x squared is equal to the square root, or sorry, not yet. It's equal to 104, and then we can take the square root. So x is equal to the square root of 104, which is approximately 10.2. Good. So most of the examples you're going to see are going to be like 1 and 2 or 4 and 5. Okay, so number 3 is a little bit different, and we are going to have to do some trig stuff in there. So it says to find the measure of the arc. So that means we're looking for the length, or not the length, but the arc measure. So remember from 10.1 that's in degrees. And then that arc measure was equal to its central angle. So if we look at this, so this angle here is equal to this arc. Okay, so if we can figure out what that angle is, then we know our arc. So I'm going to break it down and look at this triangle here. Since we're looking for an angle and it's a right triangle, we can use trig. Okay, so I'm just going to draw that triangle a little bit bigger so we can see more what's going on. Okay, so we had that this part was 8. They told us that the whole thing was 32. So that means that it's bisected to get just half of it. So we're looking for this angle here, for theta. So then we would determine if it's going to be sine, cosine, or tangent. So we're given opposite and adjacent. So remember, SOHCAHTOA, is that sine, cosine, or tangent? Very good, that's going to be tangent. This is opposite and adjacent. So we can set up our equation. The tangent of theta equals opposite over adjacent. And then remember, to get theta, you have to do the inverse. So theta equals tangent inverse 16 divided by 8. I'm just going to write that it's 2 instead of writing the fraction again. So then from there we would type it in our calculator. So if you have a non-backwards calculator, you just type it exactly how it says. So tangent inverse of 2, we get that theta equals 63.43 degrees. So remember, when we drew our little baby triangle from the beginning, we had that theta was just one half of it, but our arc actually represents this whole angle. So if this angle is 63, then that means that this side is going to be 63 too. So the whole arc AB would be 2 times 63.43, since each half of it is 63.43. So we end up with 126.86 degrees. Okay, so if you didn't understand all of what we were doing in that one, make sure you ask about it in class. I know that one's kind of tricky because we have to go back and use trig stuff. So that is it for 10.3. Werner out.